So matrix inverses. So I want to go back to an idea from the last lesson where we talked about taking a linear system of equations and organizing it into a matrix of coefficients. I called it A times a vector of unknown values and setting that equal to a vector of constant terms. So just kind of going over this to emphasize that these are matrix and vectors here. And when we're doing this, the idea is usually to solve matrix equation for the values of x that make the system true, that make each of those equations true. So let's think about how we do that when we just have numbers, okay? When we have like the scalar equivalent. Okay, I'll make my ink thin here. So if we just have the number a times number x equals d, okay, we know how to solve this, right? We would multiply both sides of that equation by 1 over a x, 1 over a times d, and the 1 over a times a would be equal to 1, so we get x equals d over a. Right? So what we'd like to be able to do is some analog of that for the matrix equation. So that's where we're going here. And to sort of set ourselves up for that, let's kind of think about what we went through there. We multiplied through by 1 over a because that is the multiplicative inverse of a. Okay, what's a multiplicative inverse? It means that 1 over a times a equals 1, okay, where 1 is the multiplicative identity. What does that mean? What's so special about 1? What's so special about spelling identity? Let's do that right first. Identity. What's special about 1? Well, 1 is the number that if we multiply 1 by any other number, its value isn't changed. Okay, so what we're thinking about right now is, do we have analogs of a multiplicative identity for matrices? The answer is yes. There is a matrix equivalent. And so if there is that, can we find multiplicative inverses for matrices? Sometimes. And when they do, and we can find them, then we can solve an equation like this just by finding the multiplicative inverse of matrix A, multiplying both sides by it, and that would give us the values of x that make it true. Okay, so that's the overall idea here. And so in the rest of this lesson, I want to talk a little bit about what the multiplicative identity is for matrices and say a few more things about inverse matrices as well. So first, the identity matrix. We call it I. And the way I looks is it has ones on the main diagonal and it has zeros everywhere else. So I'm doing a 4 by 4 I here. I's are always square. Put that in that place. Makes more sense. Here we go. So let's really make the rows and columns line up here. So I've got an example of an identity matrix. Again, it's 4 by 4. It has ones on the main diagonal. So every place where the column and the row are the same, it equals 1. Everywhere else, it equals 0. So identity matrices, you can have them any dimension you want. They're always square. So you have a 2 by 2, 3 by 3. You can have a 250 by 250, whatever. All you do to make them is you just put those ones on the main diagonal and zeros everywhere else. And the great thing about the identity matrix is, like the number 1, if we pre or post multiply any other matrix by it, we don't change its value. Okay, so A post multiplied by I equals A, and A pre multiplied by I still equals A. So this is what makes it multiplicative identity. Just in case you're wondering, right, there's an additive identity too, right? That's 0, and you could also have a matrix of all zeros that plays that role. That's nothing really more to say about that, but the multiplicative identity is a little bit more complicated. What else do I want to say about the identity matrix? Let's just convince ourselves with one little example that it works the way I say it does. So if we have a 2 by 2 matrix, make it an arbitrary one here. Those are my elements, and I multiply it by one of these identity matrices. So you can always find an identity matrix of any dimension you need to make the multiplication work. So here I have a 2 by 2 matrix. So to post multiply, I need to have 2 rows in the identity matrix. And because it's square, I also get 2 columns. So this is the identity matrix that I pick. And if I do the multiplication, I get A11 times 1 plus A12 times 0. Okay, fine, that's A11 here. For the second column in the first row, I take the first row again of the lead and the second column of the lag. So A11 times 0 is 0 plus A12 times 1. Okay, so A12 there, 1, 2 there. I think you see how this is working. For the 2, 1 element of the product, I take A21 times 1 plus A22 times 0. That gives me A21. And for the second row, second column, A21 times 0 plus A22 times 1. And indeed, it doesn't change its value. Okay. So great. Identity matrices exist. We can always find one whenever we need it. What about inverse matrices? Okay, so what we're looking for with an inverse is, given A, can we find A inverse? That's always how it's written, with exponent -1, which is would work for numbers too. Can we find A inverse such that A inverse equals I and A inverse times A equals I? So we're looking for the equivalent of the reciprocal of a number here. It is always true that if one of these things is true, the other will be true too, but sometimes both are true and sometimes neither are true. Okay, so we are not going to learn the steps in calculating the inverse of a matrix. They are extremely, well, or an arbitrary matrix. In the next lesson, we'll walk through the process for a 2 by 2, which is simpler than bigger matrices. In general, the process of finding inverse matrices is really tedious, and in contrast to finding integrals, which I think I also used that word to describe tedious, doing a few integrals I feel like gives you some insight into how integrals work and helps you sort of understand it. The process of finding the inverse of a big matrix is a lot of work. It's not demanding work, it's just adding and multiplying numbers. And I've never found a way to draw any meaningful lessons from it. It's something that computers do well, humans do poorly. So we're not going to focus on the process of finding an inverse except for a very small matrix, as I said, but I do want to talk to you about some properties and rules of inverses. Okay, so that's where we're going to go. And properties of matrix inverses. Okay, so the first rule is only square matrices have inverses. Okay, so you given an A matrix that's not square, it's 3 by 2 or something like that, don't even worry, you're not going to find an inverse for it. Second fact property here, if A inverse exists, then the inverse of A inverse gets you back to the original matrix. Okay, so again, just like it does with numbers, the reciprocal is the number you started with. Rule 3, if A is invertible, so it's the same thing as saying if A inverse exists, then so is A prime, and A prime inverse equals A inverse prime. That's sweeter than you might have expected, that the inverse of the transpose is the transpose of the inverse. If A and B are both invertible, then so is the product BA, and AB inverse equals B inverse A inverse. And the final rule is, again, if A is invertible, so is any scalar multiple of A. K is just meant to be a scalar there. So is K, and Ka inverse is 1 over K times A inverse. Okay, so the reciprocal of the scalar is multiplying the matrix, and the inverse of the matrix there. Okay. So these rules are actually pretty nice and straightforward, and they are helpful for sort of understanding algebraic manipulation of matrices. Remember, the whole idea of defining matrix algebra is that we can manipulate the matrices as single units, that we don't have to dive into the specific numbers in the rows and columns there, that we can just use these rules. So there they are. In the next lesson, as I said, I will talk about the actual process of finding the inverse for 2 by 2 matrix. That is not hard. Okay, I don't want to imply that it is. It's pretty straightforward. We'll look at that, and then we'll see how that affects regression analysis in the final lesson. So we'll see you then.